This example is a two-sample t-test, and we won't be doing pooling, so this is the non-pooled. Just make a note about that. Non-pooled. Now I know that ahead of time, but if you weren't told, then what you have to do to decide which method to use is to compare the standard deviations. If the ratio of the standard deviations is less than 2, you use pooling. If it's 2 or larger, you use non-pooling. So a standard deviation of the first sample is 2. Standard deviation of the second is 0.8, and this is clearly greater than or equal to 2. So this implies that we will do the non-pooled standard deviation version of the two-sample t-test. Let's write the hypothesis next. So the null hypothesis is always going to be mu1 minus mu2, or whatever order you wish, is going to be equal to 0. The alternative hypothesis for this example, we've got to find that here in the writing, in the statement of the problem. Here we're looking for evidence of a difference. So this is going to be mu1 minus mu2 not equal to 0. We'll use alpha at 5% because it did not tell us what to use, so this is our default. This is a two-tail test, by the way, so we will be using the two-tail probability on the t-table to get the required p-value. Just a summary on the problem statement. We have a couple of samples from a chemical analysis. We want to know if that the different mean values that are indicated represent different completion pathways. And then we have summary stats. The mean, sample 1, we'll call y bar 1, is 1.5. That's right here. Sample standard deviation, this will be S1. That's 2.0. Sample size is N1, and that's 8. Could probably make my ones a little better. Those are almost, well, you know, that's hardly an improvement. Whatever, doesn't matter. So here we have a mean of 2.7. We'll call this y bar number 2. Standard deviation here is S sub 2, 0.8, and this sample size is 10. Well, the non-pooled version of the t-test is much more compact. Here we have t is equal to y bar 1 minus y bar 2. And the denominator is the square root s1 squared over n1 and s2 squared over n2. Let's give ourselves some room to put some numbers in. Move that up a little bit. So we have t is equal to 1.5 minus 2.7. And under the root, I have 2 squared over 8 and 0.8 squared over 10. So this is going to be negative 1.2, and this is 0.7510, which gives us a test statistic on t. And let's just verify that. I'm going to grab my calculator quickly. I believe it's 1.59, but I'm not remembering clearly what the third decimal is. Not that it really matters. And what do we get? So we've got s squared. So what I'm doing on my calculator, by the way, is I'm going to figure this out, and then I'm going to figure this out, add them up, and then I'll take the square root, which might seem like an obvious thing to do, but you'd be surprised the number of times that it's not obvious. So this is 4 divided by 8, and then we have plus 0.64 divided by 10. And that adds to 0.564, and I will take the square root of that, and we get 7510. So remember that one correctly, and now we'll do negative 1.2 divided by our standard error, and our test statistic then is negative 1.59, and we're going to round that last number to an 8. There we go. This is our test statistic, and it is on 7 degrees of freedom. Because the degrees of freedom in this test are computed in a different manner from the pooled version, you take the smaller of the two sample sizes minus 1. So here, df would be equal to 7, and this would be df is equal to 9. So this is where I'm getting my degrees of freedom from. Now let's shift over and take a quick look at the t-table and what kind of p-value this produces. Now, here's row 7, right there. And our test statistic lies between these two numbers, so if we go to the top of the table, we find that the p-value then is less than 0.20 and greater than 0.10. And if you recall, our level of significance is at 5%. So our p-values are larger than alpha. This leads to a fail to reject the null hypothesis. Put the cart somewhat ahead of the horse on that one. Fail to reject H null. And there we go. Now, we should probably do a confidence interval for this one as well. Why don't we do that? We'll kill two birds with one stone in this video, just to be different a little bit. So, using these numbers, let's move up. I'm going to get my hand and get myself some room to work here. So, piece of advice, pro tip if you will, oftentimes with these you reuse the standard errors, and that's why I distinctly wrote out the standard error as 0.7510 instead of just going straight to the test statistic, because I know I'm going to have to reuse that value when I do the confidence interval. So for this one, it'd be y bar 1 minus y bar 2, so that's the estimated difference of our two samples. And the standard error here is the one we just did, is s sub 1 squared over n sub 1, and then we have s sub 2 squared over n 2. So we know the difference is 1.2. We still have to look up that critical number. We'll get that in a minute. And I know that this is 0.7510. Let's go back to the t-table now. Let's do this at, let's use 90% confidence on this. So let's go back to the t-table. And we'll go to the bottom now. Remember, our degrees of freedom are 7. So we'll come back to that row in a minute. But if you look down here at the bottom, you'll see that column corresponds to a 90% confidence level. So in the second column, this number here is our critical value, 1.89. We'll use 3 decimals in this one, so this will be 1.895. Let's come back to that. This is 1.895. So if we multiply those two numbers on the right together, we will have the margin of error. 1.895 times 0.7510, and the margin of error then is 1.423. And of course we have negative 1.2 that we have to add and subtract from that. So if we come over here, our lower bound will be this minus this, which should be negative 0.223. And then if we add those together, oh, look at me, I screwed up. That's the upper bound. I just finished adding that. Let me erase that. There we go. So negative 1.2 minus another 1.423 is actually negative 2.623. And the upper bound is what I had. It'll be positive, though. It'll be 0.223. So this is a positive number. This is a negative number. And that means 0 is in the interval. Why am I concerned with 0? Well, let's look at the null hypothesis. The hypothesis for no significant difference means that the value is essentially 0, or really not different from it. And that's what we have here. 0 is inside our interval. And the implication of that is we fail to reject our null hypothesis. There is no evidence of a statistically significant difference between the two samples, and that means this result is in agreement with the hypothesis test. And that's all there is to this particular instance of the two-sample t-test. And that ends this video.